Continuing in physical chemistry, we're now starting chapter 5, beginning with section 1. So we're going to talk more about standard thermodynamic functions of reactions. Now first let's talk about solids and liquids, the condensed phase. The standard state is the pure substance. The pressure is 1 bar, which is the same as 750 torr, or 0.987 atmospheres. Now before 1982 it was 1 atmosphere, so this has actually changed recently. The temperature is whatever temperature we're interested in. Typically, tables in books and so on, they have 25 degrees Celsius, which is, roughly room temperature. For example, it'll be written like this. The molar volume at standard state in 200. So this 200 would mean 200 Kelvin. The M means molar, of course, so it's intensive. And the naught would mean 1 bar, assuming it was made after 1982. Now for gases, the standard state is the pure gas at 1 bar, and that the gas behaves like an ideal gas, which is fictitious, and we'll talk later on about how to compensate for that when you're applying it to real-life situations. And just like with solids and liquids, the temperature is any temperature of interest. Okay, that's all for section 1. Now we're in chapter 5, section 2. We're going to talk about the standard enthalpy of a reaction. It's written as delta H for the change in enthalpy. The naught means standard state, and T for whatever temperature. So we have the delta H naught T is equal to the sum of the nu I times the molar enthalpy at that temperature for substance I. Now remember, we already talked before, last chapter, about how nu I is going to be greater than 0 for products, and nu I, the stoichiometric coefficient, is going to be less than 0 for the reactants. For example, we already did this example. So here's 2 moles of, what is that, hexane, plus 15 moles of oxygen gives you 12 moles of carbon dioxide and 6 moles of H2O. Well, this is the balanced reaction. So these are the stoichiometric coefficient, nu1, nu2, nu3, nu4. So the standard enthalpy of the reaction is going to be written like this. 12 times this for the CO2, because it's a product, plus 6 of the enthalpy molar of the standard state for the water, because it's the other product, minus 2 times the enthalpy of the molar enthalpy in the standard state of the, oh wait, that's not ethane, that's benzene. Whoops. Anyway, the C6H6, benzene, minus 15, because it's another, minus sign because it's another reactant, of the molar enthalpy in the standard state of the diatomic oxygen. So likewise, if we have H2 plus 1/2 O2 in the gaseous states going to H2O liquid, so the change in enthalpy, or the standard enthalpy of the reaction at 298 kelvins is going to be negative 286 kilojoules per mole. If we double that, we have 2 H2 gas plus O2 going to 2 H2O liquid, then the standard enthalpy of the reaction at 298 kelvins is going to be minus 572 kilojoules per mole. So it's important to realize that this per mole, it means per mole of the reaction as written. Notice it doesn't say like per mole of hydrogen or per mole of water or per mole of whatever. It's per mole as written. So you have to pay close attention to the tables. What exactly is it written to? Now, we can't have absolute enthalpies. Just like before we talked in thermodynamics, we're not going to find absolute entropies. So this pure substance, the enthalpy of formation, the molar enthalpy of formation at the temperature for a standard state is just not available. That's all we're doing for section 2. Now we're in chapter 5, section 3. The standard enthalpy of formation is the, oops, is there supposed to be a delta H? Okay. There should be delta H formation, temperature I naught. I think that's right. So F is formation, T is temperature, and I is the substance. So we're going to define an arbitrary reference state. The enthalpy of formation of an element in its reference form is the most stable form of that element at the temperature we're speaking of. For example, the standard enthalpy of formation at 298 kelvins of oxygen gas, is supposed to be diatomic oxygen gas, is equal to 0. This was arbitrarily decided. This is the reference state. So what that means is the standard enthalpy of formation at 298 kelvins for ozone gas is not equal to 0 because we used the stable form as the reference, so the less stable form is not going to be the same. Likewise, the standard enthalpy of formation of just pure O gas is not going to be equal to 0. Now for carbon at 298 kelvins, the most stable form is graphite. So that means the standard enthalpy of formation at 298 kelvins for carbon in the graphite form is equal to 0. But the standard enthalpy of formation at 298 kelvins of carbon in the diamond form is going to be different. It's 1.897 kilojoules per mole, which is obviously not equal to 0. So let's say we have this compound HCHO, which is formaldehyde. So what's the enthalpy of formation at the standard enthalpy of formation at 298 kelvins for formaldehyde? Well, it's negative 115.8 kilojoules per mole. Now, let's say we have H2 gas plus O2 gas plus carbon in the graphite form going to our formaldehyde here in gas form. Now we're assuming that our standard state, we have 1 bar, temperature is 298 kelvins for the reactants, and we're going to treat the gases ideally. Now this is theoretical, not practical, but later on we'll talk about how to compensate for that. Now RxN is short for reaction, just to, save space here. So the enthalpy of formation, the standard enthalpy of formation for the reaction, is the sum over all the substances I's of the stoichiometric coefficient I, this is a nu, remember, of the standard enthalpy of formation at that temperature and for that substance I. And like we said before, the stoichiometric coefficient is going to be greater than 0 for products and less than 0 for reactants. So we're basically going to be taking products minus reactants, just like you would do for any other change, after minus before, final minus initial. So the standard enthalpy of formation at that temperature in substance I, this has to come from a table or experimental data. So here we go, this is ethane. So we have ethane gas plus oxygen gas going to carbon dioxide and water. So what is the standard enthalpy of formation at 298 kelvins? Well, the enthalpy of the reaction is going to be 2 times the standard enthalpy of formation for the carbon dioxide gas plus 3 times the standard enthalpy of formation for the water gas minus all of this, the standard enthalpy of formation for the ethane plus the 7/2 times the enthalpy of formation for the diatomic oxygen. Now, the diatomic oxygen is in a standard state, so we know this one's going to be equal to 0. But these other ones we're going to have to look up in a table. Because remember, the standard state is only for a pure element, not for compounds. So we get the enthalpy of the reaction is 2 times negative 393.51 kilojoules per mole plus 3 times negative 241.82 kilojoules per mole minus 84.68 kilojoules per mole. So the enthalpy of the reaction is going to be the enthalpy of reaction in the standard state at 298 kelvins are minus 1,427.8 kilojoules per mole. So we got a negative energy. What that tells us is that when the reaction happens, energy is being released, which means it's an exothermic reaction. That's all for section 3.